So with the single step reduction relation in place, we can naturally talk about chaining many single steps together. So obviously to evaluate a real program, we're going to have to do a number of steps to get to a final answer, like a value or a normal form or both. So we naturally want to talk also about this idea of a multi-step relation. And we can generalize this for any relation basically, but in the case of the reduction relation, we're going to call it this symbol here, the arrow with a star on it, which means 0 or more single reduction steps. And we can formalize the notion of that using a general form, which is this multi-type here, which basically says that if we've got a relation on x's that's called R, then we can make another relation on x's, which is the multi-version of R, in one of two ways. So one possibility is that we don't make any, we don't use R at all. In other words, all x's are related to themselves in the multi-R world. So that's the 0 steps case, if you like. And the multi-step one here is saying, well, if R is related to X in one step and Y is related to Z in multi-steps, then X is related to Z in multi-steps. In other words, one or more steps in this case. So this is the general definition, so obviously we can apply that to our multi-step relation here, which is what this notation is meaning. So basically we can take step and multi it, right? So if we do t arrow star t prime, then we're just saying that it's 0 or more single steps between t and t prime, using step as the definition of the single step version. Now the nice thing about this multi thing is we can prove properties about it in general for arbitrary relations. So some obvious ones that hold are if we can make one step between x and y using R, then obviously we can make 0 or more steps from x to y, because 1 it fits into the definition of 0 or more steps. So that simple implication holds. Proof is easy. Also the transitivity holds, so we can go from x to y in some number of steps and y to z in some number of steps. Then obviously we can go from x to z in some number of steps. So that's quite useful for various proofs. Okay, so examples. So for example here we have a plus with two nested pluses, and we want to prove that we can do some number of steps to get to a constant, which is this number. So they've left the pluses in there just to make it a bit clearer. And the proof is sort of tedious but pretty easy. When you're looking at something like this, you're saying, well, there's not a single step I can do to get from P to C. So I have to use the sort of multi-step idea, and in this form you have to give the intermediate thing. So remember, in multi-step, if we go back to the definition, the two pieces you have to have are a single step between x and something, and then a multi-step from that something to the target z. So we have to come up with the something, which is the y in this case. So in the proof down here, you can see there's a with clause that says, well, this is the appropriate y for this position, which is because it's basically going to single step that piece there to a constant first. That's kind of the first thing that happens. So you can see we multi-step it, and now the first part is a single, so you have to pay close attention to whether there's a star or not on these arrows. So this one hasn't got a star, so it's a single step between those, and we can prove that with the st plus 1 and then an st plus const. Right, so essentially we made one step nested inside here. So now we have to do multiple steps to get here, and we do similar things to get that to work. A slightly more simple version of the proof is using eApply, so that you don't have to come up with these intermediate forms manually, because the wildcards will, the existential variables will let you do that. So you can get this sort of situation where there has to be something that the first thing can step to, and then you have to be able to do multi-step from it to the answer, and the identity of what it is will be revealed as you do these steps. So by the time you get to here, we know what that has to have been. Okay, so that's a lot more convenient for doing these kinds of proofs. Okay, so the rest of the proof is the same except for the apply versions. Okay, so you can have a look at their other examples here. The notion of normal form sort of fits naturally into the multi-step world, because if you think of evaluating some term t all the way, then we can consider a normal form as being what we defined before. In other words, we can't make any more steps from it, but we also have to be able to reach it from the starting point in 0 or more steps. Okay, so this is sort of normal form of is a relation between two terms, which says if you start evaluating in t and do 0 or more steps to t prime, and t prime is a normal form, then they're related using this relation. Okay, and this is getting pretty close to the sort of thing we want, where we want to be able to say, well, this is very close to sort of talking about a big step relation, because we're talking about the starting point and the ending point by applying lots of single steps to get to the ending point. Whereas the big step relation gets there in one go, essentially, logically. This gets there in lots of small steps. Okay, so don't remember what the homework is here. Yes, so the last homework is this one, normal forms unique, which is basically showing that this relation normal form of is deterministic. In other words, if you start out with a particular term and get to a normal form, there's not two ways to do that. You can only do that in one way. So, and it's a good idea to follow the start here. So don't fiddle with the beginning. Just continue the proof as it's stated here. And finally, something that's even stronger than that is this idea of a normalizing relation. So what does that mean? That means that if you start out anywhere, in other words, at any term whatsoever, there is a normal form that you can get to by following the multi-relation. Some number of, by using the multi-relation, you can get to a normal form. Right? So this is the one that's essentially saying that you can't get stuck. Oh no, it's not saying you can't get stuck. It's saying that you will never just continue making steps forever. You'll always get to a point where there are no more steps possible, and that's a normal form. Okay. So this is just a property of an arbitrary relation, right? So it just says that there's t and t prime. There is some t prime such that t is related to t prime using the multi version of the R relation, and t prime is a normal form of that relation. Okay, so what they go on now to do is prove that the step relation they have for this particular simple language is normalizing. And they do that in a couple of steps here where they give themselves a couple of congruence lemmas. So you remember congruence lemmas are to do with, say you have here a term p t1, t2, and you want to sort of evaluate t1 as much as possible. So you can say, well, if it evaluates into t1 prime in 0 or more steps, then you can just replace the t1 with t1 prime, and they are also related in 0 or more steps. So it just makes some proofs a bit easier because you can just substitute into other terms and still be in the multi-relation. And this is the one for the T2 side of the world. And if you have that, I won't go through the informal version, but you can prove using these congruence things that step is normalizing. Okay, so this is the kind of proof that programming language people like to do because they give us some very strong constraints about a programming language. This is a very simple programming language, so you get some idea of if we make it into a more complicated language, then we've got a lot of cases to deal with if we did a real language. There's only 2 kinds of constructs in this language, and we still get a proof that's 20 lines long or something. But the properties are the things that are important here. So if it's normalizing, that's a very strong constraint on programs. And essentially it means that you can't have an evaluation that goes on forever. In other words, things like infinite loops and those sorts of things aren't possible, which is not going to be true for most programming languages. Most programming languages won't be normalizing, but some subset of them is quite likely to be normalizing. Okay, stop there and come back with sort of tying the knot between the big step evaluation and the small step reduction.